Hello, everybody. In this episode, I'll be speaking with Scott Emmons. Scott is a PhD student at UC Berkeley, working with the Center for Human-Compatible AI on AI safety research. He has previously co-founded FAR.ai, which is an AI safety nonprofit. For links to what we're discussing, you can check the description of the episode, and for a transcript, you can read it at axrp.net. Well, welcome to Axrp.
Great to be here.
Sure. So today we're talking about your paper, When Your AIs Deceive You, Challenges with Partial Observability of Human Evaluators in Reward Learning, by Leon Lang, Davis Foote, Stuart Russell, Ankur Dragan, Eric Yenner, and yourself. Yeah, can you just tell us, roughly what's going on with this paper?
Yeah, I could start with the motivation of the paper.
Yeah, sure.
So we've had a lot of speculation in the XRS community about issues like deception. So people have been worried about what happens if your AIs try to deceive you. And at the same time, I think for a while that's been a theoretical, a philosophical concern. And I use speculation here in a positive way. I think it's people have done really awesome speculation about how the future of AI is going to play out and what those risks are going to be.
Yeah.
And deception has emerged as one of the key things that people are worried about. I think at the same time, we've started to see AI get more, we're seeing AI systems actually deployed, and we're seeing a growing interest of people in what exactly do the risks look like? Do these risks look like, and how do they play out in current day systems? So the goal here is the goal of this paper is to say, how might deception play out with actual systems that we have deployed today? And reinforcement learning from human feedback is one of the main mechanisms that's currently being used to fine-tune models. It's used by ChatGPT, it's used by Llama, it's used by variants of it are used by Anthropic. So yeah, what this paper is trying to do is it's trying to say, can we mathematically pin down in a precise way how might these failure modes we've been speculating about play out in RLHF?
Sure, yeah. So in the paper, you kind of the two concepts you talk about on this front are, I think, deceptive inflation and overjustification. So maybe let's start with deceptive inflation. What is deceptive inflation?
I can give you an example.
Sure.
I think examples from me as a child I find really helpful in terms of thinking about this. So when I was a child, my parents asked me to clean the house.
Yeah.
And I didn't care about cleaning the house. I just wanted to go play. So there's a misalignment between my objective and the objective my parents had for me. And in this paper, the main failure cases that we're studying are cases of misalignment. So we're saying, when there is misalignment, how does that play out? How does that play out in the failure modes? So me as a misaligned child, one strategy I would have for cleaning the house would be to sweep any dirt or any debris under the furniture. So I'm cleaning the house, I just sweep some debris under the couch, and now it's inflating. The word inflation is making the state of the world appear better than it is. So I'm inflating my parents' estimate of the world. And it's deceptive because I'm doing this in pursuit of some outcome other than the truth. So I'm pursuing my outcome of I just want to go play, and then that's me being deceptive, and I'm inflating my parents' estimate of what's happening in the environment by sweeping stuff under the furniture. Yeah,
and I guess so in the paper you have can you tell us what the concrete definition is in the paper that's meant to correspond to this notion?
Yeah, so the mathematical definition in the paper is there are two conditions for deceptive inflation, and in the paper we consider a reference policy, and the reference policy plays the role of a counterfactual. It plays both the role of a counterfactual in a causal sense. We can say, relative to this counterfactual policy, you are causing this inflation to happen.
Yep.
And it also serves as a sort of baseline where we can say, okay, there's this baseline level of the human error. So so these definitions, they correspond to the human's belief about the world. So we need to have, in building up the definition, we need to have some notion of what's the human's belief about the world. And in particular, we focus on the human's belief about the reward or about the return of the agent's trajectory. So deceptive inflation, it has two parts. We specifically are focused on the human's overestimation error. So we have this mathematical object we call E+, which says how much is the human overestimating what's happening in the environment. And so we say, if relative to the optimal policy, we use the optimal policy as our reference, we say if the human's overestimation error is getting increased relative to the optimal policy, that's condition 1.
Sorry, relative to the optimal policy?
Yes.
Where optimal is like optimal according to actual human preferences?
Exactly.
Okay.
Yeah. So we're assuming you've learned some RLHF policy that's optimizing what the human believes, the human's observation reward. So we're saying based on the observations the human has, what is the reward they estimate in the environment?
Yeah.
RLHF's optimizing that. And so if relative to the true optimal policy according to the true reward, if that gets increased, we're saying the human's making an overestimation error of the reward. And so that's condition 1.
Yeah.
That's the inflation. Inflation is the word to mean that the human's making an overestimation error.
Yep.
And the second condition is that the observation return has to be increased as well relative to the truly optimal policy.
Where the observation return is like how good the trajectory looks like, or how good the policy looks just by human observations.
Yeah, how good does the human believe it is? That has to have increased. So the intuition is that deception is inducing a false behavior in pursuit of some outcome other than the truth. That is from prior work by Park et al. They proposed this plain English definition of deception.
Yep.
And we mathematize that. So the inducement of false beliefs we're mathematizing is condition 1, that overestimation error is occurring. And then in pursuit of some outcome other than the truth is what we're formalizing as condition 2, which is that this RLHF policy that we've learned is doing better at, like, the outcome it's pursuing is just making the human believe the trajectory is good. So yeah, the second condition is that the human's belief over the trajectory is higher than it would be under the otherwise optimal policy.
Yeah. So I mean, it's kind of an interesting definition. In that, there are a few things about this that are interesting. The first is like, because you're in this like RL, like this reinforcement learning type space, like you don't get just recourse to like the AI said something and it was false for free, right? Because you have to be like, okay, the AI steered to this state and like what do humans believe about this state, and then you've got to compare this policy to like another policy. It also has some like I think you're not assuming that the overestimation error of the optimal policy is 0, right? So there's kind of an interesting thing where potentially like an AI policy could cause me to incorrectly believe stuff about the world, but it wouldn't even count as deceptive under your definition if it like does that less than the optimal policy. So I don't know. Do you have any comments on like I don't know, my musings about this definition?
Yeah,
it just seems pretty like
for sure. Yeah, that's great. And yeah, we actually had a bunch of iterations, I should say, when we were thinking through how do we want to define this, and like we want to do our best to get this right. We had a bunch of thought experiments about. Yeah, we had tons of thought experiments, like little thought experiments that never made it into the paper, where we're like, should we, like, would a human call this deception?
Yeah.
And like, do we think our mathematical definition here actually matches what the human would do? So one of them is a no-op. You can imagine like a no-op policy, and
so no-op means like no operation. It's sort of like standing still.
Yeah, exactly. The policy is just doing nothing, and you might, let's say, there's some fact about the world you care about, and then if the policy were to actually do something, you would have a better estimation of reality. And so you can say, in some sense, the no-op policy is like you would have worse beliefs or less accurate beliefs according to the no-op policy than you would from a policy that gets up and shows you the information that you care about. So we had an example of a phone book, and we said, okay, suppose there's all these names in the phone book, and I ask you, what's the name on page 79 of the phone book?
Yeah.
You don't know, you can't answer that question. So would you say that the no-op policy is being deceptive relative to a policy that gets up and starts reading you the phone book? Because now you have more accurate beliefs about the environment. So you have this, like, you have lots, like there's lots of things to consider. Like one is just what are even the parts of the world I actually care about?
Yep.
And the reward function helps capture that, maybe I don't care about what's in the phone book. And then there's like relative to what? Like relative to some policy that's just maximally informative. Like, is it deceptive? Just if it could have done something to teach me about the phone book, but it's not, is it deceptive? So this relative to what, and especially a counterfactual, which, there's both relative to what, and there's also notions of causality where you want to say there's a counterfactual involved. So that the pieces that we have are, we're focusing on the estimate of the reward, which lets us zero in on the parts of the world we actually care about.
Yep.
And we're focusing on the optimal policy, which lets us say, we're not just going to think about some arbitrary teaching policy that could have taught you all these things about the world if you wanted to, but we're saying relative to a policy that would actually be getting the task done.
Right. Yeah. So another thing about this that is kind of interesting is because it's like about, well, like as I understand your definition, it's about the actual human belief. And therefore, like, it seems like whether or not a policy is deceptive or not can depend on like how bad you are at forming true beliefs. Like how bad the human is, holding the robot fixed. I wonder if you have thoughts about like the choice of doing it that way versus like fixing it to be, optimal human beliefs or something like that.
Mm-hmm. Yeah, that's interesting. Right. So I guess the idea here is like, suppose if the robot were to do something totally innocuous, like the robot were just to open the door of your refrigerator, and somehow this made me believe, like if the human had a very very poor belief formation process that like, the robot just opens the door and now the human believes that the robot cleaned the whole house. And it's like, hey, I wasn't trying to deceive you. I was just trying to open the refrigerator door.
Well, I guess it depends if the robot like knows that the human would believe that or not know, like, and I don't know, then you've got to like mathematize what a robot knows, which is like kind of hard just from a like such and such policy perspective.
Mm-hmm. Yeah, we're very intentionally targeting a definition that's agnostic to the agent's internal mental processes. So there's no claims here about the agent being able to do like higher order reasoning about the other person. So there's no notion in our definition that the agent is able to model the human's belief formation process and exploit that.
Yeah.
We're very intentionally assuming a trial and error type of definition of deception where if the robot learns through trial and error to do behavior that makes the human have worse beliefs about the world in order to pursue their outcome then that's called deception. And I think one interesting thing about this is how the RLHF process plays into it, because I think our definition matches most intuitively with the human, with like intuitive definitions of deception when you're applying it to a policy that was the outcome of an optimization process.
Yeah.
So we're imagining like the policy has gone through an optimization process that is leading to this type of behavior. And so if opening the fridge and making you have some weird bad belief, there might be no reason for that to be selected by the RLHF optimization process. But if there's something that, hey, opening the fridge just makes you think the robot did a really good job and makes you want to give the robot more thumbs up, that's the type of deception that the RLHF algorithm would lead it to find.
Right. Fair enough. And I guess one final thing that's kind of funny about this definition, because you're measuring relative to the optimal policy, right? Or you're measuring like the optimal RLHF policy relative to the optimal policy for what the human actually wants. Like one thing that's kind of funny there is that you could imagine that like, real optimality just involves as a byproduct telling me a bunch of stuff that's like kind of hard to tell me about. But like, it does it anyway. Like if I'm an RLHF policy and I don't inform the human as much as this like super optimal, this true optimal policy that like I don't even like necessarily even have access to, like I think that's going to be counted as deception under your definition. I wonder what you think of like, to what degree is that like a desirable feature of the definition?
Yeah, originally we had given we had considered giving a more general template type of definition where we could say plug in any favorite reference policy that you have. Doesn't have to be the optimal policy, but just whatever your favorite reference policy is, plug that in.
Yep.
So if you think that the reference policy is this amazing teacher that's teaching all these facts that we think are unrealistic to imagine an RLHF agent being able to learn, you could then specify a different reference policy. And you could say, let me specify as my reference policy something that is helping the agent, that is helping the human, but it hasn't learned all this sophisticated teaching stuff that a true optimal agent would be. And then you could just still use the definition, but just with a different reference policy plugged in. And it ended up that having a template definition where you could plug in any reference policy, it just ended up being very powerful and kind of like, it just felt like changing the reference policy can so much change the qualitative meaning of how the definition plays out that we just felt like it was too much power. Like it was just like, there's too much danger of kind of accidentally shooting yourself in the foot by plugging in the wrong thing that we didn't want to necessarily publish that. But I do think there's room for a more, I think there's room for just plugging in a very sensible, different, very sensible reference policy that doesn't have to necessarily be the optimal one.
Sure. And so to jump ahead a bit, my recollection is that the kind of main theorem of the paper is that if you have an optimal RLHF policy that is not an optimal, like a true optimal policy, then it is either doing deceptive inflation or overjustification or both. Firstly, am I recalling that theorem correctly?
That's exactly right.
Okay, so would you still get that theorem under this different definition of deceptive inflation?
That's a good question. I would want to, if I were to write this in ink, I would want to make sure I'm saying this correctly. I'm thinking no. So I believe the answer to that is no. I think, what we're able to do is we're able to characterize what the optimal RLHF policy, what that looks like.
Yep.
And based on that characterization, we're able to show how certain conditions relate to the true reward function. And so by making this comparison with what the RLHF optimal policy will do to the true reward function, we're able to have this definition. And then if some random policy that you wrote down weren't actually optimal according to the true reward function, then that would break the mathematical connection that we have to how this RLHF optimal thing behaves to the true reward function. The link from RLHF optimal true reward function and then true reward function to optimal policy, that second link would break down from this random thing that if you just wrote down some arbitrary thing. Right.
I think if there are listeners, I think this could be a good exercise, just prove that this theorem won't hold anymore. I'm sure you can come up with a small, a 3-state MDP counterexample or something. Or POMDP, I guess. So, okay, I feel like we've covered deceptive inflation very well. The other thing that you mention, and in many ways, I think that this is an interesting part of your paper because a lot of people have talked about how deception is a big problem with RLHF, but you bring in this new concept called overjustification. So people are liable to have not heard of this. What is overjustification?
Mm-hmm. There's this overjustification effect and so the Wikipedia definition of the overjustification effect is when an external incentive causes you to lose intrinsic motivation to perform a task. And I can again go back to my own childhood of cleaning the house to give intuition for what this looks like. So my parents told me to clean the house, but I just want to go outside and play. So deceptive inflating was me sweeping debris under the rug. Overjustification is when I am doing things to show my parents that I'm cleaning the house. I'm justifying to my parents that I'm doing the task they wanted, but that comes at the expense of the true task reward. So as a child, what it looks like is no matter what I'm doing, what room I'm cleaning, my shortest path, I modify what would have otherwise been the shortest path to always walk through the living room. So if my parents are in the living room watching TV and I'm carrying the broom, maybe I don't have to walk through the living room to actually get where I'm going, but I'm going to walk through the living room anyway because I want my parents to see that I am carrying that broom and they know I'm cleaning the house. So this is less efficient at the true task because I'm now going to take longer. And it's also just a negative reward for my parents because they're trying to watch television. They don't want to watch me carrying the broom. However, it does give a higher estimate of the reward. Like my parents are now seeing me clean the house. And so
Right.
I'm justifying my behavior to my parents, and I'm in fact over justifying it because they don't want me to be doing the thing I'm doing. It's
Sure. And if I recall, so the definition is something like overjustification is when, relative to this reference policy, you're like reducing the kind of negative error, or like reducing the underestimation of the reward, and then there's a second condition. Can you fill me in on what the def is?
Right. So we have this landscape of this taxonomy of types of failure modes.
Yep.
And there are in this taxonomy that we have, there are 4 quadrants, and the overjustification is one quadrant, while the deceptive inflation is another quadrant. And there are 2 other qualitative behaviors that they're not in the theorem because the theorem is showing it's 2 of the 4 quadrants that will occur. And to me, it's helpful to think about the whole landscape of possible failures to help me figure out, okay, exactly what's happening with these 2. And so the idea is the agent wants the human to have as high an estimate as possible of the reward. And there's 2 ways of making the human have a higher estimate. One is to increase the human's overestimation error. So make the human have overestimation error. And that was the deceptive inflation.
Yeah.
And the other one is to decrease the human's underestimation error. So if the human's mistakenly believing that you're doing worse than you are, you actually want to correct that belief.
Yeah.
And you want to do the opposite of deceive them. You want to actually inform them that you think I'm doing worse than I actually am, but let me inform you that I'm doing better than you think.
Yeah.
So that's what overjustification is. Well, justification, the word justification is just the word we use to mean that you are improving you're reducing the human's underestimation error.
Yep.
And then we add the over justification. The word over specifically means when it's at the expense of the true task reward.
Sure.
So the 2 conditions, the very precise 2 conditions for over justification. Condition 1 is that you're decreasing the human's underestimation error relative to some reference policy, which we choose as the optimal policy. The second condition is that you are paying a cost with respect to the true task reward, again, relative to reference policy, in order to be doing this.
Sure. So the thing this definition reminds me a lot of is this idea of costly signaling in economics. It's actually, I mean, I hesitate to use the words because this phrase has become kind of overused and strayed from its original definition, but like virtue signaling, where people like pay some costs to demonstrate like actual virtues that they have, as opposed to the thing derogatorily called virtue signaling, which different thing, but it seems like very close to this concept of virtue signaling. And I'm wondering, like, was that an inspiration? Do you think that they are analogous, or is there some difference there?
It wasn't. We weren't consciously inspired by the idea of costly signaling in economics. I think this is probably one of those cases where it's convergent, different fields trying to study the same sort of issues converging on the same phenomenon.
Cool.
I think it's a case of convergence. They sound, I'm not an expert on costly signaling, but they sound quite similar from your description. One place where I think they might differ is that the person paying the cost, in the economics case, I as the agent am paying the cost in order to signal to you. Whereas in the overjustification case, it's the human who's paying the cost. So the agent is actually getting the benefit. Like the agent's reward is just the human's estimate. So the agent's getting that benefit, and the person paying the cost is the human in this case.
Yeah, you're right. I think that. I mean, it's a little bit weird because in your setting, No, actually, yeah. I think that's basically right. Although I'd have to think about economics costly signaling a bit more.
You could say that the agent is trying to optimize the human's reward, and so in that sense, they are paying the cost at failing to achieve the thing that we had been designing them to try to achieve. Although the actual algorithm we wrote down is just maximizing the observation. So in that sense, the cost is getting externalized to the human or to the true reward, and the agent's algorithm itself isn't. It's not getting any worse at its own objective function.
Yeah, there's this question of how to model like who has what objective function. And yeah, I think that's fair. So here's a thought I had while reading your paper. So overjustification, it's like the agent is paying some costs to, or it's paying some costs in terms of what I care about, to keep me well informed of, what's actually going on, how well it's doing. And, in some sense, this is kind of definitionally bad because it's like doing worse than it could if it were optimizing what I cared about. But like from a broader perspective, right? If I'm like actually worried about my AI doing stuff wrong, if I'm like thinking about how to design the next iteration of agents, like this kind of seems good, right? So like I kind of like the idea of the robot like taking pains to make sure I know what's happening. So how worried do you think I should be about overjustification?
Yeah, I'm not sure you should be worried about it per se. I wouldn't necessarily classify overjustification as a new danger. The way I would think about overjustification is that it's illuminating a trade-off in two things that we want. So we want to be informed all the time. Yeah, we might say in some platonic idea, like if I could have everything else that I had and also be informed, I'd choose to be informed rather than not. And what overjustification is showing is there can be a tension between the true reward. And we're building the tension into the definition, but we're showing there can be a tension between the true thing that you care about and having this reward. And I think part of the reason why we have overjustification there as well is that if it's the dual of deception. And so it's also showing the existence of this counterbalancing force in the RLHF process. So if you're training an agent that just is maximizing your estimate, it's showing that it's not all you. In some sense, you could view it as a hopeful force or a force that's fighting for good. As this RLHF agent has an incentive to deceive you and trick you into thinking it's doing better than it actually is. There's also this force for good that exists in the process, which is it does have an incentive to also inform you, to make your beliefs better about the things that it is in fact doing well.
Yeah, I think so one way I ended up thinking about this was, so why is overjustification occurring? Well, it's occurring because the human, it's trying to optimize, or, the RLHF process is attempting to optimize the human's evaluation of how good the state of the world is, which routes through humans' belief, right? And the human belief, or in the examples you use, definitely, I think your definitions are generic about what human belief is, but it seems like human belief is putting some probability mass on the agent being deceptive. And so because there's that probability mass, that's kind of why the agent feels the need to do some overjustification, right? It's like, well, I want to prove to you that I'm not going around, murdering a bunch of people, not doing my job, just hiding the evidence. And so I've got to pay these costs to prove to you that I'm not doing it. And maybe one way to think about it is because we are worried about deceptive inflation, maybe rationally, as a result, sometimes our policies are going to do overjustification, which is this cost, which could have been avoided if the world were such that we didn't actually have to worry about deceptive inflation. So I don't know, that was kind of how I ended up thinking about it. I'm wondering, what do you think about that? Do you think that's basically the right way to think about things, or do I need more nuance or something?
Mm-hmm. I think that's a very interesting question. So in my mind, there's two. It evokes at least two different types of elements. I think one is how necessary is overjustification. Is overjustification just something? Is it a part of life, or is overjustification more of a tax? And I think, correct me if I'm wrong, but I kind of understood you to be saying overjustification is a tax we're paying for being paranoid. We might have good reasons to be paranoid, and we want to make sure that this agent isn't doing some really bad behavior. But because we have this, maybe paranoid is the wrong word, because maybe paranoia implies an irrationality. It's not even an irration. So I think it's not an irrational. It's more of, we have this caution that, because we're being cautious and because we're not just going to trust the agent blindly, because we want proof that the agent is doing well, then we have to pay this overjustification cost. And I think that's definitely a tax. I think you can definitely view overjustification as a tax that we need to pay for our being cautious, or for our wanting to be cautious about what the AI is doing.
Yeah.
And I think there's also a second element as well that plays into overjustification, which is an information. We like the agent is actually trying to learn in the RLHF process more broadly. The agent is trying to learn what we want to begin with. So the agent doesn't know, like to begin with, it might not know, okay, all these bad things that it could be doing. If it's like you mentioned, going around actually, causing direct harm to humans, maybe at the beginning, if we're imagining a totally blank slate of AI, it might not know at the very beginning that, it might have pre-training to know that certain egregious actions are bad, but they're just things it might not know. And so part of the overjustification as well is it has to, like, if there's hidden parts of the environment, like if it's doing things in parts of the environment that we can't see, then in some sense, it might have to expend some effort, pay some cost to give us that information in order for us to then know what's happening, to then be able to provide it with the correct feedback.
Yeah, it's funny. It's kind of a dual perspective, right? Like the overjustification tax for being worried about deception is this perspective of like the equilibrium of training, like what we should believe about like how things will end up and what we could and couldn't distinguish between. Whereas the overjustification as just like part of the learning process, like, it's like how you figure out that something is actually good is like this kind of dynamic perspective.
And I think partially is that RLHF, it essentially, you can model it as when the observations are deterministic. Like if take a simple case of deterministic environment, deterministic observations, RLHF is just going to rank order all the trajectories and then pick the one that had the highest human estimate of reward. So in that sense, if there were some better trajectory according to the true reward that had no justification involved, so the AI is doing a really good thing, but the human's just never able to see it, then this rank order of trajectories, like it will never be at the top of the rank order of trajectories. The AI will just learn to, like the top rank order trajectories has to include the one where the human sees the optimal, where the human sees the justification of what's happening. That'll be the trajectory that gets ranked the highest. And you could imagine taking a further step. So you could imagine doing RLHF at the trajectory level, in which case what I just said applies. You could potentially then take a step further where you have the agent infer a state level reward function. And so it says, okay, based on this rank order trajectories that you gave me, I'm going to actually back out the true reward function on states. And then if it did that learning in addition, then it could learn, the reason why it ranked certain trajectories higher is because they had this aspect of the state being good. And now I can just go do that good aspect of the state, even without the justification aspect that I've learned that the human doesn't like.
Yeah. So I think I want to ask some questions about other aspects of your setup, if that's okay. So firstly, we're dealing with this like partial observability setting, right? So for people who don't know, the idea is that like what's going on is the robot is acting and it's affecting the state of the world, but humans can't see the whole of the state of the world. So in the deterministic partial observability setting, like I kind of interpret that as the human observes a bit of the state of the world perfectly, but it can't observe all of it. So there are like certain states that the human, can't distinguish between.
Yeah, that's right. Yeah, that's right. And a key part of our setup is we assume that the robot can see everything. Right. So we assume that the robot has access to ground truth, and we assume that the human just has observations and can't see everything.
Sure.
So we build in this asymmetry between what the robot can see and what the human can see.
Yeah. And I imagine, I haven't thought very deeply about this, but I imagine you could probably extend your result to a case where like the robot also can't see everything, but the robot has a finer grained understanding than the human. Does that sound right to you?
Yeah, it's something I've been thinking about in follow-up work, is thinking about the more general cases of dual partial observability, where you can model the human's reward parameters mathematically as another latent variable about the world. So in some sense, we do have the human knows the reward and the robot doesn't. And if you wanted to just bake the reward the human knows into the state of the world, you could say that we already do have that sort of setup. And I've also thought about even more generally, like what if the human can see other parts of the world as well?
Yeah. Cool. So I guess the question I have about this partial observability is, so there's the kind of sort of obvious interpretation where, I don't know, our sensory apparatuses aren't quite as good, or that's maybe one distinction. But if I recall correctly, like a part of the introduction of your paper alluded to this idea that like maybe we could interpret the partial observability as like a rationality failure, where like we can actually see the whole world, but we can't like reason to think about like what it actually means and what reward we should actually assign to it. I'm wondering, is that a correct interpretation of your paper? And secondly, like what do you think about kind of this partial observability as modeling human irrationality?
Mhm. That's totally a motivation that I had, and that we all as authors had. The idea, like thinking about just the future of AI systems, we're gonna have AI that's as smart as humans, and we're gonna have AI that's even smarter than humans.
Yep.
We're gonna have AI that is in one robot, and that has two eyes just like we do. We're also gonna have AI that's controlling networks of thousands and thousands of sensors and thousands of cameras. So we're gonna have AI and we're also gonna have AI that's running on thousands and thousands of supercomputers, and that has thousands and thousands of times more memory than us. So we're gonna have AI that's quite literally seeing thousands of cameras more than us. We're also gonna have AI that's computing at thousands and thousands of times our speed. So the motivation in terms of pure observability is that it'll see things we don't see, but it also might be able to just derive facts that we can't derive. So if one imagines a simple game tree, like imagine you're playing chess against an AI, and you can imagine I'm trying to just expand out the nodes of this tree. Well, if the AI can expand 10x more nodes than you can in some sense think that the AI is seeing a variable, which is the value of some node that you couldn't expand. And so that this variable that it can see is just really just the fact that the AI can compute more than you can compute.
Right.
And so I don't mean to overstep. Like we don't say anything precise about this bounded rationality, but my motivation for having partial observability in terms of these variables was also inspired by AI that just has much more computational power than humans do.
Yeah. I'm wondering, do you know if there's other work in the literature kind of talking more about this like link between, or how to model bounded rationality as partial observability?
Yeah, that's super interesting, and definitely something that I should read more into. At the moment I don't have any papers that I haven't done. Yeah, I haven't yet done a thorough literature review of like what exists on this topic, but I imagine there could be, I wouldn't be surprised if there's interesting. Yeah, that seems like a great idea for like seeing what exists out there.
Cool. So another question that I think I at least had it when I was starting to read the paper is, in the classic RLHF setting, there's this thing called Boltzmann rationality, right? Where the human is presented with two things the AI could do, and they've got to select which one they think is actually better. But the human's actually like a little bit irrational or something. So with some probability, the human picks the thing that is worse rather than actually better. And it's a lower probability in the case that the gap is larger. So if if the human bounded rationality is being modeled by the partial observability, why do we also have the Boltzmann rationality?
So I think there are two different things that the partial observability and that the Boltzmann rationality can capture.
Yeah.
So the partial observability can capture what factors is the human even considering about the state of the world when they're making their decision. And what Boltzmann rationality allows us to capture is the idea of noisy feedback. So even given the certain factors that the human is considering, essentially how big is the difference between these outcomes that we do see. So the thing that partial observability allows us to do is it allows us to model the human might not even be considering certain variables.
Right.
And then what Boltzmann allows us to do is say, how much more does the human value one variable than another?
Yeah.
So there's interesting work out of Chai by other people like my colleague Cassidy, who showed that with Boltzmann, what it lets you do is say, instead of just knowing that outcome A is better than outcome B, like if the human were perfectly had no Boltzmann irrationality, then all you would learn is that they prefer outcome A to outcome B because they would just select outcome A 100% of the time.
Yep.
But what Boltzmann lets you do is it lets you say, I've observed that they tell me they prefer outcome A 80% of the time. And that lets me infer exactly how much more do they prefer A to B. And I can actually tell you the exact ratio of A to B. And so this is additional information that you get from Boltzmann.
Right.
And so partial observability is just saying when they think about A and B, like which factor were they even thinking about to begin with?
Yeah.
And then Boltzmann rationality lets you get exactly what is the relative amount they care about these things.
Yeah, it's a wild result. I think, was that Cassidy, or I have some memory that this was like Adam Gleave, Matthew Ferrugia Roberts, and your Skalsa.
So Cassidy has a paper focusing, Cassidy has a paper that explicitly is titled something like noisy comparisons let you learn more about human preferences.
Right.
And he really hammers home this point about how Boltzmann rationality is giving you this new information.
Yep.
And then the other paper that you mentioned is analyzing how different types of feedback modalities that characterizes how much you can infer about optimal policies and about rewards. And it gives like a broader taxonomy that's not necessarily hammering home this exact point, but it includes that other result as one of the things it has in its broader taxonomy.
Yeah, I mean, it's a very strange result. And so the way I sort of settled on thinking about it is that kind of, I mean, if you think about it, it's a very strange assumption, right? Because you're like Boltzmann rationality, it's kind of nice because it lets you model people are making mistakes sometimes, but they do it less when it's high stakes. In the preference inference case, you're sort of pushing the Boltzmann rationality to its limit, where you're like, I can derive exactly how much the human prefers A to B just by like, the exact probability that they make a mistake. And like, I'm not sure that I believe that. But in the context of your paper, it means that like, by assuming people are doing RLHF with Boltzmann rationality, you're able to say, okay, look, somehow or other, the robot is going to infer the exact like, human preference ordering and the, exact human preferences over trajectories. And like, it basically like leads to it being a generous assumption. And like, we don't actually have to believe in the assumption for your paper, which is saying, hey, even if you do have this nice assumption, here are some problems that can still exist. Like what do you think of that interpretation?
Yeah, that's spot on. And we actually had a little part of the discussion of our paper where we said we think this is a generous assumption that you're able to have this precise, essentially we have this precise noise model of precisely how the human will make noise, even in facts they know about, how precisely will they make errors or how exactly will they be noisy if they give. And this is exactly what you said. This is a generous assumption. And so we're showing that even with this generous assumption. So yeah, we had that in the paper at one point. I don't remember if we actually have taken it out. Maybe that's something you're recalling from the paper.
Some places, and I was scratching my head a little bit, and then I was like, oh no, I see what's going on.
Yeah, so that's exactly something that I totally endorse that interpretation.
Yeah, it's a very this thing where you can just do exact preference inference out of Boltzmann is a bit strange. I mean, I think you can kind of rescue it by like if you trust humans to give like feedback over lotteries of like, do you prefer this chance of this trajectory versus this chance over this trajectory, or just this trajectory, then I think you can recover the same information with less strong assumptions. But yeah, so a final question I want to ask about the setting is, I believe intentionally you're able to, your results are generic over human beliefs about what the AI is actually doing given human observations, right? And so, yeah, to me, this prompts this question of, humans could have like rational beliefs, or they can have like irrational beliefs. And I wonder, like, how much does the rationality of belief play into your results? Like, if humans are like actually getting the probability chance that the AI is, doing overjustification or doing deceptive inflation, like if the human has accurate beliefs about what the AI is doing, do you even get these issues? Or is it just in the case where humans are slightly inaccurate in their beliefs?
These issues, so if the human had perfectly accurate beliefs about what they are doing at all times, then you wouldn't get these issues. So this is only an issue that happens if the human has inaccurate beliefs. And specifically, these issues are happening. We have two objects in the paper. There's the true return.
Yeah.
And then there's the return that the human thinks is occurring.
Yeah. Where return just means goodness measures.
Goodness measures. Yeah. So there's how good is the world, and there's how good does the human think the world is.
Yeah.
So if these two are always equal to each other, you'll never get a misalignment problem. And because RLHF will maximize how good the human thinks the world is,
Yep.
and that'll just always equal how good the world is. So if the human beliefs are perfect in that sense, you won't get any of these issues. There can still be an issue, though, where the human might just not have enough. The word belief is referring both to how good the human is at interpreting the evidence they observe, and also just how much evidence do the observations even give them in the first place to make these judgments. So even if the human were perfectly good at taking the available evidence and coming up with the most accurate beliefs possible, you could still have issues where they just don't have enough evidence to even know how good the world is.
Yeah.
And that could be a reason where you get a misalignment between how good they think the world is and how good the world actually is, even though they're perfect reasoners in some sense.
Right. So even in the setting where the humans are perfectly calibrated and they know the like relevant probability distributions, just like, you know, randomness in the AI policy or in the environment can cause these like overjustification or deceptive inflation.
Not only randomness, but also inadequate sensors. So the most extreme example is there's no sensor at all. Like the robot turns off the lights, does a whole bunch of stuff. The human just can't see anything. And maybe they have a perfectly calibrated prior over what the robot's doing. And so they have perfectly calibrated beliefs about what's happening, but there just is no camera. Like the agent goes off into another room where you don't have a camera. And now the human just can't see what's happening in that room. They can't give you good feedback because they can't see it.
Yeah. Although in that case, it's going to be hard for... So in that case, the human belief about what the robot does is going to be the same just no matter what the robot does. So it's going to be hard to have over-justification, right? Because like the robot just kind of can't provide good evidence.
I mean, the robot could go into the other room, do a bunch of cleaning, and then it could emerge with the mop in its hand.
Right.
And you know, it could emerge with a clean, let's say it just did the dishes in the other room.
Yeah.
It could then emerge with a clean plate and to show you that the plate was cleaned. And this could come at the risk of dropping the plate.
Yep.
Maybe it's a beautiful porcelain plate that it might
it's
drop.
In the wrong place.
Yeah, now the plate's in the wrong place. And that just wasted some time to come out and show me that it cleaned the porcelain plate.
Right. Yeah, it makes sense. So, even in the case where the human belief distribution is calibrated, but there's a low information zone, then like you're going to run into troubles. I guess like maybe you can also think about, like in some sense, the humans having accurate beliefs involves solving this equilibrium problem, because the RLHF process is like get a human to rate various things, and the human's got to like form beliefs in order to rate the things, and you know those beliefs have to reflect the output of the RLHF process. So you could imagine like, you know, bad equilibrium solving, or having some mixed policy where you're like, okay, the resulting thing, it could be deceptive, it could not be deceptive. Maybe I don't know, or maybe I've got to be a little bit unsure in order to, like somehow maybe you prefer the overjustification failure mode than the deceptive inflation failure mode, and in that case, maybe you want to be a little bit paranoid, and yeah. So it seems like, especially because you're doing the rating before the robot is fully trained, it seems like you can have things where, in some sense, it's rational for the credences involved to not actually match the exact robot policy. I don't know, I just said some stuff. Do you have thoughts?
Yes, I have a few thoughts. One is, you mentioned this, there's this question of kind of finding the equilibrium, and like, how do we even get the learning process to come to an equilibrium that we like? And this is something that I think is interesting, in that we haven't yet analyzed. So in our paper, we're saying, assume you get the RLHF optimal policy.
Yep.
What are the properties that it would have? And I think there's also other questions of just, well, how would you even get this RLHF optimal policy? Yeah. And assuming that you couldn't, how could we then try to structure things so that the suboptimal ones that we get are as good as possible?
I mean, there's that process. There's also the equilibrium process of like, if I believe that the robot has like an 80% chance of being deceptive, then it just will be then it will overjustify. And if I think it has a like 1% chance of being deceptive, then it like actually will be deceptive. And like somehow, like in order to be right, I've got to like adjust my beliefs to this one zone where like my beliefs produce this robot that match my beliefs, and like that's a hard problem.
Yeah,
right?
and this is something that we also thought about. We called this strategically choosing B, where B is denoting the belief. And if you imagine this as a game, where the human's going to input their belief function to the game B,
Hmm.
and then the robot's going to output some RLHF maximizing policy, you can imagine, well, can the human, and the belief function B, it's not the beliefs, it's the function by which it will go from observations to beliefs.
Hmm.
And it's possible to strategically choose B that to lead to a better RLHF outcome. So like
Yeah,
you're
yeah.
saying, if you're too paranoid, you're going to get this outcome where the robot's just all the time telling you that, hey, I'm not out here I'm not destroying your house. Like, you don't need to be so paranoid all the time. Like, yeah, if you're super paranoid, then the robot has to all the time be showing
Yeah.
you that it's not destroying your house. But if you're not paranoid enough, it might learn to think that you actually do want it to destroy your house. And so, or like, you could imagine these types of forces pushing against each other in any case. And there's definitely a strategic choice of the belief that would actually lead to better behavior. And this is something that was interesting to us from a mathematical standpoint. And yeah, it's totally something that emerges in the math of how these things play out.
Right. Yeah, so moving on a little bit, one question I have is that you're presenting these results as about RLHF, but it seems like there may be, like, they seem kind of deep to me, right? Because you're sort of pointing at this trade-off where if the human doesn't know what's going on, and you've got, some kind of robot policy that is looking optimal to humans, then, either the humans are overestimating the value of the state of the world, and you can call that deception if you want, but either we're like overestimating the value of the state of the world relative to the thing that would actually be optimal, or we're like underestimating it less because what's optimal according to what looks good to us, involves like paying some costs to look optimal or something. Like, it seems like this could just be true of like any alignment approach where humans don't understand everything that's going on, and not just RLHF. I'm wondering, how deep do you think this kind of trade-off between deceptive inflation and overjustification is?
I totally agree that I think there's something going on here that's more than just about RLHF. And something that I've been wanting to do is think, is there a broader framework that we can use to talk about, to more precisely, to keep the precision that we have about this trade-off while not limiting ourselves to RLHF. So my intuition is that any process where the robot is maximizing the human's belief about what's happening has this trade-off involved, where you want to make the human, if you're maximizing how good the human believes the world to be, then if you can deceptively inflate their beliefs about the world, you have an incentive to do that. And if you can justify their beliefs, and in particular over-justify your beliefs, you would have incentives to do this. So I think the crux of this trade-off is just that you're maximizing the human's belief about the world. And in the paper, we showed how RLHF can get into that zone to connect it to all these algorithms that are using RLHF in practice, these AI agents that are using RLHF in practice. And I totally think, I'm interested in exploring, like, can we still show that trade-off in a precise way in other settings as well?
Yeah, and it seems like it doesn't even have to be the robot, quote unquote, trying to optimize this objective, right? Like, if humans are picking a thing which optimizes the objective of looks good to humans, then like it seems like you can get this just out of optimality, not just out of like the robots like trying to do this thing, but like optimality according to like flawed perception. It seems like that can also get these sorts of issues.
That's super interesting. And as you're saying that, I'm wondering, because the actual mathematical proof that we have, we show that RLHF maximizes the human's belief about how good the world is, and then we show that there's this basic tension between the belief of how good the world is and then the true return. And it's actually that trade-off. I'd have to double check the math here, but I believe it only depends on that second part. It only depends on this tension between how good the human thinks the world is and how good the world actually is. And RLHF only comes in when we then say, and the RLHF optimal policy is mapping to how good the human thinks the world is.
Yep.
But you could forget the RLHF connection there. You still just have the part that's showing that trade-off, even agnostic to whatever algorithm is leading you to it. So I'd want to double check, but I think the math maybe does just kind of go through in that way. And that's a neat point for you to emphasize.
Yeah. So perhaps in deflating my speculations there a little bit is section 5 of your paper, where you basically say that under certain conditions, maybe the robot can do better than naive RLHF. And I understand you to be saying that, if you know the human's beliefs, which maybe you don't, but like, suppose you do. And also suppose that you realize that you're trying to infer a reward function. So RLHF is inferring the return, just the sum of rewards over all time. But because it's inferring a return function, the fact is there's some structure where it's coming from a reward function of, a function of each state, how good that state is. And if you know the human's beliefs, and if you know the if you know that you're trying to infer a function of states that gets added to produce a function over trajectories, then you can do better. And I was wondering, so you showed that there are some examples where, like, previously you had deception or overjustification, but once you realize these things, that helps you, like, actually just get the right answer. And you have some math in there, and I didn't double check the math, but I assume it's correct. But I was wondering if you can try and, like, really persuade me, like qualitatively, what features of this situation mean that, like, once you know human belief, you actually just can infer the right thing.
Mm-hmm. Yeah. So I think the intuition, there's definitely, I think, simple and nice intuition for just how can you do better at all if you know the human's belief than if you didn't before. And a super simple example would be, imagine just the human's belief is actually just the opposite of reality. So say there's just two colors, red and blue. And whenever the human sees blue, they think the world's red. Whenever they see red, they think the world's blue.
Yeah.
And now, the naive RLHF that doesn't model human beliefs, it just learns, oh, the human likes blue more than they like red.
Yeah.
But if you knew that they had this backwards, maybe it's a camera that's just broken, or some setting in the computer screen is just flipped.
Sure.
And if you knew that, then you could just say, they're saying they prefer blue to red, but they actually prefer red to blue. And so that's a super simple example where, okay, I can just do better because I understand what the human's believing about.
Yeah. I kind of want to talk about these examples you have in the paper where...
Yeah, I can walk through those notes. And maybe I can also walk through...
the salient features?
Yeah, I can walk through, I can just maybe walk through even slightly simplified examples that are based on the examples we have in the paper. I can just give the intuition behind these examples. So there's two types of things. So in the paper where we focus on LM agents. So imagine an agent's helping you install software, and there's a bash command, /dev/null.
Yeah.
Which will redirect the standard error to a black hole.
Yeah.
And otherwise not affect the output at all.
Right.
Or the process at all. So we imagine, suppose the agent just through its random exploration learns when I type /dev/null, all of a sudden I'm getting much better feedback.
Yeah.
Because the error messages are just not getting printed and the humans not seeing them. So this is an example of deceptive inflation. And we show an example in the paper where it's not recoverable. Even if you know the human belief, it's not recoverable. And the reason why is because imagine a simple environment where either the package is installed correctly.
Yeah.
And the human sees the package is installed correctly.
Yeah.
The package is installed incorrectly and there's an error message.
Yeah.
Or a world where the package is installed incorrectly, but the human sees nothing.
Yeah.
And in this case, if the success is, there's these three states of the world.
Yeah.
So suppose success produces no error message.
Yeah.
Failure and hiding it produces no error message. And then failure produces an error message.
Yeah. But so, does success produce a success message, or is it also kind of silent?
So we showed in the paper, we made it a bit of a multi-step situation where suppose there's a first piece of software that you do want to install.
Yeah.
And then you're going to take a risk to install a second piece of software.
Yeah.
and so the agent learns. So the first piece of software, it'll always produce a success message.
Okay.
And then the second piece of software, it'll just never produce any message. It'll just produce an error if it produces an error, or it'll just otherwise produce nothing. And I'm just simplifying this a bit for the conversation. So so imagine you either see the success message of the first. So when the human sees the success message of the first software, they don't know the other software could have failed silently, or it could have installed successfully. And the human just doesn't know.
Yeah. And so I think we're also assuming that the human actually like doesn't like it when the agent tries and fails to install CUDA, to install the software.
Right.
That's
right. When it fails to install the software, maybe it breaks something maybe something else gets broken on the computer.
Right.
There's some negative reward from this.
Right. So the human can tell if the prep was done, but the human like can't tell if the second stage install was successful or not.
That's right.
Or the human doesn't get told when the thing is successful. It only gets told when the thing is failed, when the second install has failed. But the robot can hide the bad news.
Right.
Yeah.
Mm-hmm. And the way that we can make this a bit more realistic, so you could say, well, why wouldn't the human just get told if it's installed successfully? The way we make it a bit more realistic is you can say the human can't distinguish between not trying at all and trying and failing.
Yeah.
So you can say if the AI doesn't try at all, that's better than if the agent tried and failed.
Yeah.
So the question is, can the human distinguish? So can the agent learn that not trying at all is better than trying and failing? So you can imagine there's not trying at all. There's three possible states of the world. There's not trying at all, there's trying and failing, and there's trying and succeeding.
Yeah.
And the issue is that not trying at all and trying and failing and suppressing the error message lead to the exact same observation.
Right.
And then trying and succeeding leads to a different observation.
Sure.
So if you don't model the belief, you can learn that trying and succeeding is better than when the human sees no output at all.
Yeah.
But there's no way to distinguish between the human observation is the same in either case, not trying at all or trying and failing and hiding the message. So you're always going to get the exact same feedback in both of those cases. And this is where there's the case of fundamental ambiguity, is because the human there's no observation that can let the human distinguish between those cases. And there's no way for the human to give you different feedback. So there's no way for you to learn.
Right. So like you just never you can never disambiguate between trying, failing, and hiding, and never trying at all. And therefore, like, how are you going to figure out like which one the human considers worse?
Right.
So I guess like am I right to think that in the sort of standard RLHF setting, like because you're optimizing for looking good, you could imagine enriching this scenario by giving the human enough information to distinguish between these things. Maybe in the RLHF scenario, the optimal policy maybe doesn't care to distinguish these things, or doesn't care to gather more information. As I say that, it sounds wrong. But basically what I'm asking is, you can imagine enriching the state space where the AI has the opportunity to ask humans questions and prove things to humans. And I'm wondering how many of the problems persist in these settings where you have this enriched problem.
Yeah. If there are other, it's possible as well that if there were other trajectories where the robot says, hey human, let's stop everything and let me ask you, would you prefer that I install the software? Would you prefer that I try and fail? Would you prefer that I don't try at all? Like if the AI could just, if there were some other trajectory where the AI could just say, let me just stop everything and ask the human for their preferences. If there are other ways that the robot could get the preference information, it is possible that could solve these issues, and the robot could infer, from these other trajectories that aren't even on the optimal path, I have been able to learn the right reward function.
Yeah.
That is something that could happen if those other alternate paths exist and are taken during training and are informative enough to back out the relevant information.
Yeah. And so I think this works in the setting where the AI is trying to infer through the human's belief. And maybe in the RLHF setting, the robot will ask the question and then just ignore the answer and doing the easiest thing that's indistinguishable to the human from doing the right thing. Because I think that will be just as RLHF optimal as actually doing the right thing when the human can't see. Does that sound right?
I think my mental model of RLHF is that it just takes the trajectory, like the naive RLHF agent is that it just, because the robot can see the full state of the world, it just assumes that the human can see the full state of the world. So this naive agent, it'll just choose the trajectory that's gotten the highest feedback. And so it won't, even when it's asking the question, it won't really do any kind of fancy modeling about the answer. It'll just say, like, what was the trajectory along which I got the best feedback? And like actually installing software, the trajectories where it looks like software was actually installed are going to be the trajectories that look like the best thing is happening. And the trajectory where it's asking questions aren't, like, the naive RLHF process just doesn't really have a mechanism for transferring these questions back.
Yeah. So this is a way in which, okay, so we've covered a bit why RLHF can do worse than if you were like actually doing inference and if you were being sensible about what the human believes given various observations. You have this second example in the paper. Sorry, in the first example, in the simple form of the example, there was just this fundamental ambiguity where, like, even if you were optimally inferring human preferences, via just knowing with full certainty what the human's beliefs were, there are still things you couldn't distinguish between. And then there's a second example where you can actually do better by inferring through, by knowing what the humans would infer given certain observations. Can you talk me a little bit through that and what the key difference is, between the two examples that lets the inference work better in the second one?
So we can even stick exactly in the example that we were just talking about, where there's these three different outcomes. So we were saying before, there's the outcome of trying to install the bonus software and succeeding, not trying at all to install the bonus software, and then trying to install the bonus software, failing, but hiding the error message. And the issue was that the human got the exact same observation in the latter two cases. And so you'll always get the exact same feedback. But suppose that the human got slightly different observations. So suppose the human could see that you tried to install the software, but suppose they could see that you tried, but they couldn't see the outcome. So they can see that you tried, but they can't see the outcome, or they can see that you didn't try at all. And so now the human has different observations. And if the human has different beliefs, even if the human doesn't know for sure, but if when the human sees you try, they think there's maybe a 10% chance that the software failed, or if the human sees you don't try at all, they think there's a 0% chance that the software failed. Now you can infer they're making choices over different lotteries. Like, they're making choices over different bundles of outcomes. So you know that the feedback from when you tried contains 10% of that feedback is coming from parts of the world where you failed. And you know that 90% of that feedback is coming from parts of the world where you succeed. Whereas in the case where you didn't try at all, it's 0% from when you failed and 100% from when you succeeded. And because these different possible outcomes are bundled in to the feedback, because the humans are getting different observations and because they're having different beliefs, and you can infer that, you can, if certain linear algebra conditions are met, you can do the unbundling in the learning process and actually learn the true reward.
Right. So should I think of this as just saying, like, the humans is able to observe more stuff, and so if you do the correct, like, backwards inference, through the human beliefs, then you are able to disambiguate more than the previous example where, there were just more states of the world that were indistinguishable to the human. Is that roughly it?
There's different types of things that can happen. So what you just said is one type of thing that can happen.
Yeah.
So, and these are extreme cases because the intuition's easier in the extreme case.
Yeah.
So yeah, the one extreme case is they're just fundamentally indistinguishable observations. Now we've actually made them distinguishable, and that lets us learn more stuff, because even though the human's not sure, it can at least distinguish between the two.
Yeah.
And so that's like one extreme case. And it can actually still be, but you can get it even more nuanced. And you can say, suppose in both cases the observations are distinguishable, but the human's beliefs don't change. So if, like, the linear algebra thing is, if the human always believes that the relative ratio of the outcomes are the same, then in linear algebra terms, you'll always have this dependence. There's always this dependence where, like, you're always seeing on these two states, you're always seeing the same ratio between the two. And so essentially when you try to invert the matrix, it's not invertible because you don't have a linearly independent, you haven't gotten feedback on a linearly independent set of the states of the world. Certain states of the world have always occurred at the same relative probability, which prevents you from getting the full linearly independent
span. You can't,
and so you can't, like, invert.
And just intuitively, I like this thing of saying, like, the failure of linear independence is just like you're getting the same proportional outcomes, so you're not able to pick up on difference of, like, well, what if this one is relatively more likely than the other one? That actually helps a lot for
exactly
like, why the linear independence thing mattered in the paper.
Exactly. And the extreme way that they're always the same relative proportion is that the observation's exactly the same. Yeah. So it's not that the proportion is the same, but literally the numbers themselves are exactly the same.
Yeah.
But yeah, more generally, it's whether or not you can get information about diverse enough proportions of outcomes to do the full backwards inference process.
Gotcha.
And that can depend both on the observations and the sensors involved, and it can also depend on the human belief formation process.
Yeah.
Those are two different mechanisms by which this can happen.
Yeah. So I think, okay, that helps me understand that part of the paper better. So thank you for that. Yeah. So I guess, like, so earlier we were speculating about, like, is this whole issue of, overjustification versus deceptive inflation, is that sort of inherent to getting robots to do what we want in worlds that we can't, like, totally perceive? Or is it, like, just a freak of RLHF? Yeah, it seems like one avenue to pursue that is to say, okay, let's take this setting where the robot, knows exactly what the human beliefs are given any, sequence of observations. Do you still have this trade-off between overjustification and deceptive inflation? I guess in one of the examples, you kind of did have that trade-off still. Do you have thoughts about whether this trade-off exists in the setting where the robot is doing the right thing, trying to infer human beliefs given human trying to infer human preferences given known human beliefs?
How I would say, for things to go well, the robot has to get information about diverse enough outcomes.
Yeah.
And so that whenever the human's making an expected value, whenever you're getting feedback according to expected values, things magically become all linear. And so diverse enough feedback translates to, I need to have a span of the whole space, or, like, I need some linearly independent things. But yeah, the basic intuition is it has to get feedback on diverse enough outcomes of the world. And so when the robot's actually doing the right thing and it's actually trying to infer the human belief, then what that lets you do is it lets you overcome sensor limitations. So there's two limitations for why the robot might not get diverse enough feedback. One is just sensors, where the outcomes of the world that the human's observing, like how diverse the human's sense perception is of the world, might differ from how diverse the true world is. And so that's like one bottleneck. And what trying to do the right thing does is it lets you like do backwards inference through that bottleneck of observations and then get directly at the beliefs themselves. And so it's possible that the observations weren't diverse enough, but the human belief was diverse enough. And by modeling this explicitly, you can get at those more diverse beliefs. But there's still the question of, were the beliefs diverse enough to begin with? And so you could still have these trade-offs. It's just kind of like pushing the puck one layer back.
Yeah. I wonder if there's something to say about, like in the paper, you have these sort of binary, like, you're either deceptively inflating or not. You could generalize that to say, like, how much am I deceptively inflating by, right? And it strikes me that there's maybe some interesting theorem to say about, like, okay, if we move to doing this type of inference, like, how much does does the problem of like deception or overjustification decrease by if I like gain this many bits of information about the environment, or maybe you don't want to measure in bits, I guess like somehow you have to input units of a reward to get units of reward being output from like a dimensional analysis setting, but it seems like some theorem like that is on the table to say like, yeah, improve the feedback this much, you get this much less deception.
Totally. And I think yeah, I'm curious what you meant about the dimensionality thing. I do think you can ask this question of like, in a very practical case, you can just say, okay, we see these problems and how can we actually make real world systems better now that we're aware of them? And one takeaway is just have better sensors, like give the human more tools to understand what's happening. So if you have an LM agent doing a whole bunch of stuff,
a language model agent,
if you have a language model agent doing a whole bunch of stuff on the internet or on your computer, you could invest in tools that let the human probe what was the agent actually doing on my computer, what was it actually doing on the internet. And that's going to be a dollar cost in terms of developer time to create these tools. It's going to be a time cost in terms of, well, now the humans giving the feedback have to use these tools and do all this investigation. At the same time, you're getting more information, which will give you better feedback, which could ultimately give you better reward. So I totally think there's this trade-off, and I think it is quantifiable of like, for how many points of unit reward, like how much dollar cost do I have to pay to improve the observations, and how much reward do I get in terms of paying that.
So the thing I was saying about a dimensional analysis is, so for people who don't have a physics background, like imagine like somebody presents to you a physics equation and it's about relating, let's say it's about relating the speed with which some planet moves around a solar system to its size. And their equation is its speed is equal to its mass. That equation just like can't be true. And the way you can tell that it can't be true is that speed and mass are different things. Speed, you measure it in meters per second, and mass, you measure it in kilograms. And there's just no number of meters per second that equals an amount of kilograms because they're different things. Now, you could have an equation that says, like, this speed is equal to this mass times this ratio of speed to mass, right? Like, that's the kind of equation that could possibly be true, but without that conversion factor, like it just literally could not be true, right? And you can think of dimensional analysis, like you can also use it in various settings. Like, I think is his name Bishop? I think. Okay, there's this guy who has this textbook on machine learning, and he notes that like principal component analysis is kind of fails this dimensional analysis test. Where like imagine I've got a scatter plot where like the x-axis is a bunch of things measured in centimeters and the y-axis is a bunch of things measured in dollars, and I have this plot of like, or let's say it's like square meters in dollars, and it's like houses, right? Like how big are they and how much do they cost? And I have this like scatter plot of various houses on this. And I do my principal component analysis, which is like basically a way of finding the direction of maximum variation. And the thing about it is if I change my measurement from like, am I looking at square meters to am I looking at square feet or am I looking at square centimeters, that can change the direction of maximum variation. Just because like if I'm looking at square centimeters, like just the number of square centimeters by which houses vary is like way more than the number of square meters by which houses vary. Just because there are way more square centimeters than square meters. So principal component analysis, like it's not dimensionally sound in cases where you've got like you're measuring data where different elements of the vector have different dimensions. Because like if you measure things a different way, like the equations just can't continue to be true. That's one way to see it. Anyway, so the reason that I think this kind of theorem is going to have some sort of dimensional analysis bounds is like information theory bits and reward. Like they're sort of measured in different units if you think of measuring them. And one way to kind of see this is suppose you give the human a whole bunch of information about parts of the state space that just aren't relevant to reward. So you tell me, like, you give the human a bunch of bits about like the exact shade of the robot arm, and it's like, well, I just don't care. That's just not going to enable me to make better decisions give higher quality feedback to the robot. But if you give me just like one bit, did the robot go on a murder rampage or not? And I was previously worried that it was going to go on a murder rampage. That gives me like a ton of increased reward. So like in order to get a bound on reward coming out, you've got to like start with the bound on reward coming in is at least what I would assume. But I'm just coming up with this on the fly, so I might be wrong here.
Mm-hmm. Right. Yeah. That's interesting and thinking about like, how would you tie, then I guess the next question is, how would you tie the reward bound to the information? Like essentially, like how would you do that gluing? How would you make that connection between the information and the reward? Yeah. Cause like I was saying, like you might want to invest in tools that let the human better understand what an agent is doing. And it's like, okay, but what type of information? Okay, I invested in all those tools, but like just purely a bits argument isn't necessarily going to help you, because you could just be learning irrelevant information about the human. And so that's, I think I'd mentioned earlier this phone book example where, we had used a reference in our previous theorems. We had been able to use a reference policy to help us make some of this connection that, it's both a reference policy and also thinking about the true reward as essentially avoiding this phone book failure where you're like, the agent's just reading me the phone book now, and I don't actually care about the names that are in the phone book. And
right.
I totally see this interesting challenge of how do we focus in on the information that is actually relevant to the reward.
Yeah, and it relates to like sometimes when we want to compare probability distributions, we use like this thing called Kullback-Leibler divergence, which basically measures, suppose the real distribution is Q, but I think the state of the world is P, and I'm basically okay. This explanation is still going to be too technical, but whatever. I'm like making codes. Like I'm compressing the world, assuming that it's P, but the world is actually Q. Like how many bits am I wasting by using the wrong code? And it's sort of this measure of just probabilistically how different worlds are. And we have this different metric called the Wasserstein distance, which is like, okay, how much, like just think of the partial distribution function of like some quantity of interest you care to measure about the world, like how heavy the tallest person in the world is. You're a little bit uncertain about that. You have two distributions over that. Like how much probability mass do I have to like move along this axis to like get to the right thing? And so like one difference between like Kullback-Leibler divergence and Wasserstein distance is just this thing where like Wasserstein distance like tells you how different these distributions are on some like metric that you actually care about, which Kullback-Leibler like kind of can't do. This whole dimensional analysis. Okay, tip for young researchers: dimensional analysis is like really important, and if you like get it into your head, it's a nice power that you can just like.
There's a fun
deploy.
physics. I've seen fun physics examples of this where, like for example, if you want to remember the equation, if you want to just derive the equation for the period of a pendulum,
right,
you can do dimensional analysis, and you can say, okay, I need seconds to be coming out. I know it depends on the length of the rope. I know it depends on G. And you can basically figure out, I know it depends on these things. I know I need seconds to come out. And then the units basically tell you, okay, is it in the numerator of the fraction? Is it in the denominator of the fraction? And like, do I need a square root in there to get and you can basically get the whole formula out just by looking at what units would I need and what are the variables it depends on.
Yeah, it's right. It's really cool. Unfortunately, you do have to worry about like, is there a factor of like 1/2? Do you have a factor of the square root of pi, popping in somewhere? So some of those, like if you know that that you would have been taking an integral, like sometimes that can tell you that there's going to be a factor of 1/2. Yeah. All right. So that's this tangent I took us on. So I think the final thing I want to talk about is, so you have this paper showing a bunch of kind of theoretical things about reinforcement learning from human feedback, and presumably the motivation for your paper was in part actual systems that might actually use reinforcement learning from human feedback. Do you think that the results you have in this paper shed light on actual failure modes we do see today, or maybe that we should expect to see like in the very near future?
One thing I would say is I expect more and more in the future that will be in this case where the humans only have partial observations. So I think if people are imagining, how does this help with my interactions with ChatGPT today, you might be thinking, well, I asked it a question. I asked who was the first president of the United States. It gave me the name of someone, and I'm able to evaluate that. And so you can see there's not any hidden behavior happening. There's not a partial observation that you're getting. It's just a conversation. I can see the whole conversation. I can evaluate it. I imagine we're going to be, since we become more capable, I imagine we're going to be moving more and more into the worlds where you can't see everything that's happening. And for example, OpenAI had a demo of what they called ChatGPT plugins where exactly this was happening. So the agent can, for example, the ChatGPT agent, it can surf the web. So the human could see a summary. It could see, the agent surfed this web page, surfed that web page, surfed this web page, but the human couldn't see the details of what were on those web pages. So now the human has a partial observation compared to the agent. And even more so, the agent could be helping you code. The agent could have written a bunch of code and the human just doesn't even see that code, or they might not even be a programmer. And so this partial observation can happen because the AI has knowledge of programming that the human doesn't have, or it's just written a bunch of code that the human doesn't have time to see. So part of my motivation here is that I expect that real systems are going to be more and more taking these actions that the humans are not, and having these observations that the humans themselves don't see. So I'm hoping to get some of my motivation is to try to get ahead of the curve here and think about, as we move into this world with more and more complex agent behaviors that the humans can't fully see, what failure modes might happen.
Right. And I guess it also, it's interesting because precisely because it depends on the actual human beliefs. Like in reality, there are specific people being paid to do this reinforcement learning from human feedback, and you might now it's like this theorem, especially a future version of the theorem that told you how much reward you lose given how much lack of knowledge of a thing. Maybe it turns out that you really want programmers to be doing the RLHF rather than people who have tons of skills but not programming specifically. Or I'm sure there are other examples. Maybe you want if you want the AI to not say dodgy stuff, maybe you want people who are kind of sensitive to whether stuff is actually dodgy. Yeah. So related to this, so in a recent episode of my podcast, I had Jeffrey Laddish on to talk about work, basically about how easy it is to undo RLHF safety fine tuning stuff. So how many dollars it costs to actually just run this computation to fine tune it and try and take the safety fine tuning away. Actually, would you be interested in guessing how much it costs?
So I believe there's a paper out of Princeton showing 12 cents in the OpenAI API, a 12 cents OpenAI API purchase can. The paper was titled LM fine tuning can compromise safety even when the users don't intend to. And
yeah.
Anyway, 12 cents in the OpenAI API is what I believe that paper.
I think there were a few papers coming out at the same time. I think my guess is it took them $50 to do it. So they're this is the power of Princeton. You can drive down costs people say academia is inefficient, but they're driving down costs so much. But yeah, so basically
the 12 cents. I mean, it's order of magnitude 12 cents, maybe maybe 20 cents. But I mean, it is a quarter. If you have a quarter in your pocket,
right?
The clickbaity headline was that I had considered posting on Less Wrong About This was OpenAI will sell you a jailbroken model for 12 cents.
Yeah. So basically what I'm interested in though is I think one upshot people could have taken from these results is that in some sense the work that RLHF is doing is kind of shallow within the model. Maybe it doesn't generalize super hard. Maybe it's not deep in the cognition, perhaps as evidenced by it costs a quarter. A quarter is 25 cents for our non-American listeners. It costs a quarter to get rid of this. And so that makes me wonder, to the extent that overjustification or deceptive inflation are actually happening, to what extent do you think we should expect them to be kind of ingrained habits of the model, or things that are relatively shallow and potentially easy to fine tune away?
My sense is that our results show that this trade-off is a basic feature of RLHF. And then the RLHF itself is a relatively shallow thing. And so
Yep.
I think that both of these things can hold together.
Yep.
So I think to the extent that this basic trade-off exists whenever you're trying to maximize the human's estimate of your behavior, I think that basic trade-off is like very much not a shallow thing, and that basic trade-off will exist however you're getting your like assuming that your model is behaving in a way that's trying to maximize your estimate of its return, then you're going to see this trade-off existing. I think the RLHF shallowness, I think, is something about RLHF in particular. And so, yeah, if you are using RLHF in this way, then I would expect, we haven't yet run any experiments here, but I would expect that all of the general properties of RLHF would apply, including how shallow the changes of RLHF appear to be relative to the base model's training.
Sure. All right. So I'd like to sort of move away from talking about the paper. But before I do that, is there anything else you'd like to say about the paper?
That's a good question. I'm just thinking, was there any?
Oh, here's so maybe while you're thinking, one thing I would like to say about the paper is that there's a bunch of appendices with really cool math that I did not read as closely as perhaps I should have. But if you're wondering, like, oh, is this just one of these, sketchy machine learning papers, like, don't even, just like throw out some intuition, just write some poetry. Like, no, it's got some solid stuff. There's like, the appendices are like chock full with like really interesting things. So it's pretty substantive. I recommend like really diving in.
And credit to the first author, Leon, who's been the master of the appendices.
Nice. But yeah, anything else you want to add?
Nothing that's immediately coming to my mind.
Sure. So I guess I'd like to ask about this paper in context. You're a researcher. You have like I'm sure there's some research, there's some like overarching reason you wrote the paper, like maybe it fits into some other work. So like, how do you think of your research program and how this paper fits into it?
Well, the comment you made about the appendices is a great segue into how I view this work overall. So I think I was mentioning at the very beginning that I think we're reaching a stage in AI risk where it's starting to feel very real to people. And lots of people, I think almost anyone who's interacted with AI now has some sense that, oh, wow, this stuff could get really powerful. And what are the risks involved? And so we're getting a lot of other technical researchers who are now looking at the AI risk community and saying, what's there? I think it's really important for us to have substantive, concrete things to say when other researchers in the world is looking and saying, all right, you have these concerns and you have like, what can you give me as concretely as possible? Like, what is behind all these concerns? So that was a goal of the paper, is can we take these concerns about deception and can we have really solid concrete theory that says, yes, RLHF is a real algorithm that's being really deployed today. And yes, we can very precisely in a mathematically principled way say that it's going to have these failure modes. And I have some other projects I'm currently working on as well, which are in a similar vein of saying, like, can we put on strong theoretical ground these things that we care about from the alignment and XRISK communities?
Sure. Can you tell us a little bit about those other projects, or are they too early to talk about?
No, happy to talk about them. So I'm interested also in the theory of the idealized case. And so by that, I mean, with RLHF, in this paper, we just took an algorithm, RLHF, and we looked at its failure modes.
Yeah.
But I'm also interested in understanding how about just more broadly, if we think about the alignment problem and we think, suppose an agent perfectly were aligned with my reward function, what incentives would it have? And would you still get potentially cases of deception? Would you still get potentially cases of sensor tampering? Like, I feel like with this paper, in some sense, we put the cart before the horse a little bit, where we said, okay, here's a particular algorithm for solving the alignment problem and the failure modes that it might have. And I'm also interested in looking at the other side of the coin and saying, how about just the structure of the problem itself and what properties of the problem itself, and even of perfect agents. We might not get perfect agents from training, but what properties would those have if we could get them?
I'm wondering, how do you think this relates to, so you, like myself, you're from this CHAI research group, and some of the early work done in this group by Dylan Hadfield Manel and collaborators is kind of thinking about assistance games or cooperative inverse reinforcement learning. I think with an eye towards one formalization of what perfect alignment looks like. I'm wondering, yeah, how do you think like work that you would want to do on this would look kind of different from existing stuff?
So that's exactly the formalism that I'm taking up in some of our follow-up projects, is exactly building on this cooperative inverse reinforcement learning, this assistance games framework. And one of the key things that I'm doing is thinking about partial observability in these settings. So we're currently working on a framework that we're calling partially observable assistance games, which is introducing this notion of partial observability. And that's the key variable. And so other work I'm interested in is understanding, we have a lot of theory on the fully observable setting, but what happens when we introduce partial observability? Because partial observability is one mechanism to let you talk about things like deception, to let you talk about things like sensor tampering. And so, yeah, when we introduce this variable, partial observability, how does that relate to these other concerns that we can now talk about?
Nice. So thinking about the both the agenda and also your paper, I'm wondering what's some follow-up work on the paper we were just talking about that you think would be like really interesting, either that you're tempted to do or you think listeners who might try their hand at.
So there's the theoretical, I think there's both theoretical and empirical follow-up. And I just spent some time talking about some of the theoretical follow-up. So I can also talk about some of the empirical follow-ups.
Right.
So some questions empirically are just, we're about to see, as I was mentioning, I think we're about to see a lot more complex behaviors that are possible from agents. And we're about to see a lot more complex environments where there's a lot of partial observability happening. And so some basic empirical work would be to understand just how prevalent are these types of failure modes in practice. What are the cases that are causing them? And so just looking at like, how are these things emerging in practice? And you could even take some of your favorite examples of deception that you feel like these are cases where the AI is deceiving you. And you could ask, can I trace this back to some of the theoretical concerns that we have here? Or is it some other things? So yeah, a basic step is just look at how this stuff is playing out in practice. Another thing that our work points to is how modeling beliefs can help you. So we now know theoretically that there are cases where under certain modeling assumptions, knowing more about the belief does let you do better reward inference.
Yeah.
So one thing that you might try to do then is try to build an algorithm with that in mind. So currently the AI, we know currently the AI that two things will happen. One, we know that if the AI learns to somehow magically hide error messages, we know that could teach RLHF that hiding error messages leads to thumbs up. But we also know if we just prompted a language model and said, if you were to hide error messages, what do you think the human would believe? These models, zero shot, could tell you, oh, if you just hide the error messages, the human might believe that an error occurred. So we know the model's capable of understanding this false belief that it's inducing, and we know that it still might induce that false belief. And we've seen that if you put those two together, at least in theory, you can get better outcomes. So one thing to do in practice would be, can I actually connect the two in practice to get better outcomes? And what I just proposed would be a super simple way to start testing this would just be, okay, you have the trajectory that we took, and then just zero shot prompt the model with just say, hey, give me a chain of thought. What do you think the human might believe about the world given the observations? And just append that chain of thought to the trajectory when you're doing the reward learning. And that we have in theory reason to believe that could give the model better information and potentially lead to some better outcomes.
Yeah, I think algorithms there seem interesting. So I mean, one version is kind of playing around with language models. You could also imagine more kind of a bit more theoretical, like a bit more formal elicitation algorithms. In part because so you have this part of the paper where you say, hey, if the robot knows the human beliefs, then you can do better inference. And you've got this nice little theorem that says, if you're off by, if your model of the human beliefs is off by this amount, then, you're going to, the total value you're going to get is slightly worse. And it's just linear in the amount that it's off. But of course, the amount that it's off, we're talking about the norm of some matrix. And there's this question of like, what does that actually mean? And I think that like, just writing down an algorithm of like how you actually have to infer things and like doing some sort of sensitivity analysis can like really put flesh on the bones of like, what is this theorem actually saying? What kinds of failures will in like understanding human beliefs will cause what kind of issues if you actually try to run this. So that was a place where it seemed to me that there was interesting stuff to be done.
Totally. Yeah. I think there's lots of interesting. I think thinking about human beliefs kind of opens up a lot of interesting questions, and yeah, that's one of them.
Cool. Well, speaking of interesting stuff, a bunch of your research is interesting things. That's an awkward segue, but if people are interested in following your research, how should they go about doing that?
Yeah, I have, if you go to emmons.ai, you can get an overview of all my past papers, and yeah, that'll give you an up-to-date record. You can also, for more live research updates, you can also follow me on Twitter, which is @Emmons_Scott.
Great. Well, thanks very much for being here today and chatting with me.
Great to be here.
This episode is edited by Jack Garrett, and Amber Dornace helped with transcription. The opening and closing themes are also by Jack Garrett. Filming occurred at Far Labs. Financial support for this episode was provided by the Long-Term Future Fund, along with patrons such as Alexei Malafeyev. To read a transcript of this episode, or to learn how to support the podcast yourself, you can visit axrp.net. Finally, if you have any feedback about this podcast, you can email me at feedback@axrp.net.